to make a, let's say, a drastic change of topic. So, as you probably have seen, many of the problems, of the definitions that you have seen here in this course can be treated in a very parallel fashion. For example, everything that concerns the TF-IDF vector space, so representing documents as vectors, well, it requires, for example, the computation of the inverse document frequency of a term, meaning you need to know how many times, in how many different documents the same term appears. And also term frequency, of course, requires for every document to know what terms it contains, and also let's say we need to compute normalization factors and so on. So, in particular, let us focus on the IDF point. The inverse document frequency requires you to look at all documents and remember how many times you see a term. Okay, this problem falls within a category of parallel problems, or problems that are naturally parallelizable, that some people call, well, I'm not going to write it, but embarrassingly parallel problems. Meaning that it's very easy to devise a parallel solution. However, the problem is, what does it mean that it's easy? It means that for most of the computation, you don't need intercommunication between the parts. For example, you can have many, if you have many computers, you can give a small batch of documents to every computer. Each of the computers will compute, of course, a partial inverse document frequency, so it will compute the count within its own set of documents, and only at the end you need to merge everything. So there is no need of inter-processor computer-to-computer communications during the bulk of the work. To do this, there are some specific frameworks that have been proposed, and what I'm going to describe today is the MapReduce framework proposed by Google a few years ago, and now available in a large number of different languages and platforms. So the idea of this framework is that, well, it is precisely addressed to those problems that don't need continuous inter-process communication, but they can just be based on a very specific synchronization time. So maybe it's easier to show you how it works. For example, suppose that we want to compute our inverse document frequency. And suppose that we have a number of machines that, well, every machine receives a number of documents, Now, when it comes to counting terms within documents, I mean, sorry, we are in the IDF. So actually we want to count how many documents a term appears in. This machine can output its own partial count. It means that what it can output is a list of tuples of pairs where it associates to every term the number of documents that contain it. So the number of documents corresponding to that term. Okay. So of course this computer will output lots of these. Every machine outputs its own list. And everything up to this point is completely parallel. Machines can operate in a completely independent way. Here, of course, we need some work to aggregate these lists of tuples output by every machine. We can do it in many different ways. What the MapReduce framework does is let's call it sort and aggregate step, where all tuples output by every machine are sorted by term, and then they are aggregated so that the output of this step, let's see it as many outputs. Every output corresponds to one specific term and the list of how can I? You see, the idea is that the same term will be output by different machines, possibly all the machines. So let's say that this is the number of documents that contain term T in the subset of documents that were given to machine 1. This is number of documents containing the same term in machine 2 and so on. Well, it prepares. The sort and aggregate procedure will prepare this list for every term. One term and then the list of corresponding outputs from all the machines. Of course, the sort and aggregate function will output one list for every different term that is found as first member in all the tuples that are output by the initial computers. So it's going to output many of these lists. These lists are collected in batches and fed into possibly another set of machines, or maybe the same machines that run also a different part of the algorithm. But, for example, in this case, what do the machines need to do in order to compute the IDF? Basically, they need to add these numbers. So every machine will output lists in the form term sum of all the number of documents containing the term. And this is actually the result that we want. Of course, the number of documents is not the IDF. We can assume that they will compute a logarithm or take the inverse of that, but fundamentally we need to know the overall number of documents. Okay, this is one example. As you can see, here we have basically two phases where the machines, where our algorithms are used. This phase, which is called the map phase, where all terms contained in all documents that are passed to the computer are mapped onto a number. If you have done some functional programming, you probably know that map is the standard name of a function that, given a list in input, produces a possibly equal-sized list in output where a function is applied to every element in the function. So this is more or less what this step does, although it's not really a mapping in the sense of functional programming. While this phase is called reduced because it receives a list in input and it produces a single value as corresponding output, like the generic reduced function in functional programming. Okay. So the idea of the MapReduce framework is that the part that actually does the heavy work, which is usually the one beside here, is provided by the framework. The framework provides here a distributed file system. Okay, let's call it the DFS, distributed file system, where your input data are stored at the beginning of the algorithm. Of course, well, distributed file system means, you probably know that, it means that, okay, files appear from a logical point of view to be equally accessible as if they were in the same device, but they are actually distributed on different machines. With, of course, some constraints about, there are many issues with replication, consistency, and so on. So, the distributed file system must take care of data replications in the case that a machine requires a file that is not on the same machine. It requires in that case also consistency. If there are two copies of the same file, they must be the same. If you make modifications on one, they should be atomically propagated to the other, and so on. When you write down a MapReduce program, you basically need to provide these two pieces, this part and this part. Maybe now we can see, now I'll try to, well, let's say, formalize things a little in order to make it clearer. So, okay, let's say that in order to define a MapReduce program, we need to provide a map function that receives as an input basically, map is internally is defined as a template. A template, so we can write it like that. Oh, no, it does not suffice. In the most general definition, map operates on key value pairs. So, let's write it like this. When we define a map function, in the most general case, we need to define it on 4 types. And the map operates by receiving as an input key value pairs like this of the first 2 types, possibly a list of them. I don't know if you're familiar with this syntax to indicate 0 or more of them, a sequence of them, and generates as an output a new list of key value pairs. For example, well, in the IDF case, it received as an input, well, it received documents as inputs. But documents can be seen as, well, one single document can be seen as a sequence of key value pairs where the key identifies the document, so it's the same for the same document, and the value is a single term in the document. So that the map function receives lots of these key value pairs. Of course, the actual implementation can be easier than this. We shall see examples. And what does it put as an output? Key value pairs where keys are terms and values are integers. Number of documents that contain that term. Okay, so this is the general setting of the map function. Now, these key value pairs, the key value pairs that are output, are sorted by the system and aggregated so that all pairs that contain the same key are aggregated together and provided to the same reduce process. The idea is that a reduce process depends on, okay, is a template. The types that are used in this case are, okay, the same key as the output of the value of the map function. It operates on the same type of value as this, so it takes as an input something that has to do with the same types as the output of map, of course, and can possibly generate a new type as an output, even though usually it will be the same as this. Of course, the input will be received in a different way. One map process receives one single key value associated with a list of values. In our case, one reducer would receive just one term and the list of occurrences that were output by all mappers about that term. And it will produce as an output well, in general, one single value of possibly another type. Let's see one very simple example, simpler than the IDF example. For example, suppose that we want to simply count the number of occurrences of a term in a whole set of documents. Okay, it's slightly different from the IDF requirement. Not the number of documents it appears in, but the number of times it appears in. So it can be counted multiply within the same document. It's a bit of a simplification just to see how the algorithm works. So suppose that at the end we want to obtain a list that for every term we have the number of occurrences of that term in our list of documents. Okay, so it's just count terms in our document set. In this case, the mapper okay, it's going to operate like this. It has okay, as an input, let's say the first type is document ID. So we can expect it to be a natural number. The second type is a term. What is a term in our case? What type is it? We can assume it's a string. or maybe the documents have already been tokenized and indexed, so it may also be a document ID, a term ID, so another integer. Anyway, suppose it's a string. So take your preferred notation as string, for example, okay, a list of characters in the alphabet sigma, which might be a set of UTF-8 codes or something like that. The output of the mapper will be, of course, we get a whole list of these, will be a list of pairs where the key is the term and the output is a number. And the mapper will work in a very simple way. Every time it receives as an input the ID of a document and a string representing a term, it will just output a string associated with number 1. So, for every word in every document that is passed to the mapper, it will just count 1 for that word. If the same word appears twice, 3 times in the document, then 2 or 3 of these pairs will be output. For example, suppose that the mapper is given these 2 documents. So the document 1 is, as usual, Alice loves both. And the document 2 is, well, let me keep the same example as a few lessons ago. Okay, 2 documents like this. Okay, the mapper is going to receive all of these terms as inputs associated with different keys. So, for example, the set of pairs that are input to the mapper are, for example, 1 Alice, 1 loves, 1 Bob, supposing that the ID of the first document is 1, 2 Bob, 2 hates, and 2 Alice. Okay, these are the key value pairs that are input in our map function. The corresponding output of the map function, okay, since we want to count the number of occurrences of terms in documents, we just discard the ID information, the document ID information. We don't need it for our computation. And the output will be simply, for every term in input, the term will be output with a count of 1. Now, of course, these two documents may have been to the same mapper, or they might as well be associated to different mappers. This depends on the framework implementation. For example, some implementations just give one document to every mapper. No two documents are given to the same mapper. If two documents must be processed by the same machine because you don't have enough as many machines as documents, then two different map instances are created for the two documents, either in parallel or sequentially. Okay, anyway, this can happen on different machines, on the same machine, on different processes, on the same processes. The framework will take care of this. You only need to know that given this input tuples, you get these output tuples somehow. Then these output tuples that represent partial counts, in the sense that every existing term is associated to the count 1, replicated if it appears more than once. This is given to the sort and aggregate procedure. This procedure will put together all tuples with the same key value and generate a single tuple associated to the list of values, in this case, for example, 1, 1. Then finds Bob, associated to 1, 1. Then comes Hayes, associated to just 1 because there is just one tuple starting with Hayes, and then logs. Again, just with 1. Okay, now each of these tuples is sent to a reduce process. So that our reduce process, in our case, will be a word, just a moment here, we have Cartesian product, a word and a list of integers, and an integer will be output. So given a string S and a set of counts n1, n2, up to nk, what we output is actually the sum of all the nks. So the output of the reducer in this case will be 2, in this case will be 2. Here another instance of the reducer will output 1, and here another instance of the reducer will output 1. Finally, the framework will take the key value and the value that is output by the reducer, and will generate Alice 2, which is the final result that we want. We want to know that the term Alice appears twice in the whole set of documents. Then the framework again, it takes Bob and 2 and will output Bob 2, AIDS 1, and lots 1. And these final results will be stored again in the distributed file system as the result of our algorithm. Okay, is it clear? So the idea is that there are a few problems that can be described in a MapReduce framework. Many of these actually appear in the you see in document indexing and so on, because they were proposed by Google, because they have mainly that purpose in creating this kind of documents, this kind of framework. But it actually appears. Actually, MapReduce is now used in many different contexts. Of course, I repeat, what I presented here is the general case. So, what is the most general definition of the map and reduce processes? Different frameworks have slightly different implementations of map and reduce. For example, I still have to decide if tomorrow in the laboratory we will see something about the Java implementation rather than the Python implementation. But for example, one of the most common restrictions is that one document is provided to different documents are provided to separate mappers. This means that, for example, in the Java version, the Java framework and also the Python one are based on the Hadoop project by the Apache Foundation. So if you want to have a look at it or try it for yourself, so this is a possible starting point. So here the definition is slightly different. For example, a mapper receives as an input the whole document, meaning that the map definition in the case of Hadoop we can say that it is actually restricted to the output values. The idea is that as an input we receive, well, I don't remember well, so maybe tomorrow we will see exactly how how it is. Anyway, we are going to receive something that is an iterable list of these values, or possibly also just a text file where we need to tokenize in order to get the words. So in general, we only have input values, while the document ID is implicit in the fact that the mapper only receives one. Here, you see the reducer, in general, only needs an output value, not an output key. The idea is that the framework assumes that the output key is exactly the same as the input key, because the reducer only works on one single key value item, where the key is one value, and actually the value is a list of objects. Then the framework automatically adds the key to the reducer value, but nothing prevents us to define, if we want, also a general key here to be added here. Okay. Okay. You can probably notice that, well, you see this algorithm, this flow from the original document to the final word count, you should be convinced that it actually works. The problem is that you probably see that it's not very efficient. You see, in particular, here, if a term is repeated often in many documents, well, it has to travel the network in order to be merged in a distributed way. Okay, maybe I can delete this. I mean, suppose that, okay, documents are fed to different mappers that are possibly machines all around the world, or maybe all in the same department, but again, they are different computers. These documents are English language documents, so every mapper outputs lots of tuples of the kind the one. Simply because the word the appears in many times in all documents. So different computers all output the same, along with many other tuples, of course, but they also output this tuple very often. And remember that at the end, here we have the sort and aggregate step, which is handled by the framework. What we should get at the end from all these tuples, coming from different machines, we should have a single tuple with the, and then a list of ones, one for every occurrence of the in every document. Of course, sorting things in a distributed environment is a rather complex work. Okay, so what can we do here to at least slightly alleviate the work of the sort phase? One thing that we can do is to make a preliminary sort and aggregate phase at machine level. So suppose that, okay, these are machine boundaries. Okay. In this first machine we had two documents that were given by, to two different map processes. Here we have another bunch of processes, and also here. Okay. Actually, if here, before sending these tuples out to the network, we sort and aggregate them locally, we will end up with a single D, for example, it appeared okay, 3 times here. Okay. Also here we have a local sort procedure that outputs D and the overall number of times the tuple Z1 appears here, and so on. So here, the sort procedure is now easier, simply because, of course, here we worked on a certain number of machines, and every tuple will appear at most once per machine. So here, instead of having as an output D and then a list of ones, we have D followed by the list of times the word D appeared on each separate machine. Okay, this is a simplification of the algorithm, of course. This local reduce step is actually called the combine step. So that actually, in this particular case, we found it appropriate to use the same reduce step also for the local reduction process. The idea is that in the general case, the framework can define three different functions. The map function to be executed on the input documents, and the reduce function to be executed on the aggregated tuples to generate an output, but also a combine function that is operated locally in every machine with the same inputs as the reduce function. In the case of word count like this, combine and reduce were exactly the same function. In general, we can assume that they are different. Let's see. Okay, questions up to here? Okay. Let's see a slightly more complex no, forcing a more complex algorithm. Let's see how we can write a pseudocode of the MapReduce functions in the case of term count. So the idea is that our map function receives as input what we can assume to be an iterable list of tokens. Okay, so let's say that we have a list of tokens as the input. Well, not tokens, let's say terms. So this is the input of our function. How does the map function work? So the idea is that for each t in, assume that in is a keyword, so this is actually our document. So for each term in the document, we output, the map function should output, usually the function is called emit. What do we emit? A couple, a pair, composed by the term t and the number 1. This is all our mapper needs to do. The reducer it basically receives a term t and a list of integers. Let's call it L. And of course, all that we need to do is to add up for n in L, add n to S, and at the end we emit the value S. Okay, so this is a more or less confused pseudocode of what I mean by a map function and a reduce function. So, if we want to put this into the Hadoop framework, of course, the two parts, these will be methods to be defined in two template interfaces that are called mapper and reducer. You need to specify what types the template must be specialized on, and so on. Okay. Now, suppose that we actually want to compute the IDF, the inverse document frequency of the term. Instead of counting terms in documents, we want to compute the inverse document frequency. So, what modifications do we need to apply to this? you see the main the main problem here is that if we want to count the number of documents the term appears in, we cannot count it more than once within the same document. So we need to we need to emit this couple only if it's the first time that we see this term within the document. If we assume that map is called independently for each document, for example, it means that we need to keep in mind what terms have already been visited, been seen. So for example, here we need to maintain a list of terms. Let's call it visited. Okay, if this were Java, I should tell it that it's a new list initially empty. Let's assume that we generate a list, an empty list of terms, and here we can. So if T appears in the list of visited elements, sorry, if T does not appear in the list of visited elements, then we emit T1. And we add T to the list of visited elements. Okay, this is the only change that we need to do in order to have to make sure that a term is counted only once per document. Of course, we should be a little more efficient. This is not going to be a generic list, but probably a hash table so that it can be searched very efficiently, or rather than sequentially, I mean. Next, okay, here the reduce will receive as many ones as there are documents containing a given term. And here, rather than emitting directly the sum, we will emit something that is can be defined as the IDF, for example, 1 divided by 1 plus the logarithm of s, or something like that. Okay, so we go there. So here we count the number of documents, and here we aggregate the number of documents and directly emit the IDF. Of course, if we write a reduce like this, it cannot be used anymore as a combine, because in the combine we want to keep the sum, not to transform it with logarithms. So we could define a combine function which is basically the same as the reducer, but where we only emit the sum s as before rather than transform it with logarithms. Okay, here the idea is that every mapper is going to output a term at most once, because it operates on one document. All the mappers operating on the same machine are aggregated with the combined function. The results of the combined function are then again aggregated and sent to the appropriate reduce question.
Yes. About the combine. First, the emit should be also emit the term, because
we assume that the framework takes care of that. I mean, the term is unique. So here I'm assuming that the framework is going to take this and glue the term in front of it. Anyway, you're right. It's clear if I write it explicitly.
And also in this case, it's not useful to use the combine because the map output it for a term only one term.
Yes, if we assume, but we can assume that the different mappers are executed on the same machine. So we can combine the outputs of different mappers. Of course, one single mapper is not going to output the term more than once. In fact, it really depends on the implementation. If a mapper receives more than one document, then of course we need to review also the map function, because we need to reinitialize this list every time we go to a different document, or we need to take different lists for different documents, and so on. Okay. Well, I actually assumed that it would take longer, so probably I skipped something that is very important. Or I have been too pessimistic about this topic. Okay. Let's see. We could see maybe some other case in which this MapReduce framework can be used. For example, okay, one other possible application of MapReduce, maybe the one that was most important for Google, building a reverse index, an inverse index of terms. So binding terms to documents. So given my set of documents, the 1, the 2, and so on, I want to bind every term, T, to the list of documents, the list of documents that contain that term. And possibly maybe also the position of that term within the document. So consider the same example as before. I want to create an index where Alice is associated to D1 in position 1 and sorry, D2 in position 3. Okay, because here is where the word appears. Again, Bob appears in D1 in position 3 and in D2 in position 1. Next, AIDS appears only in document D2 in position 2, and loves only appears in document D1 in position 2. Okay, I want to have this output. Actually, you see here, well, you should already understand that this is more or less the output of the sorting and aggregation phase. Okay, the idea is that if we define the mapper as something that takes as an input well, in this case we need to assume that the mapper also knows about the document ID, because we need its output. So suppose that we have also an integer ID here. Actually, in the Hadoop implementation, you don't get the ID as far as I remember at least, as an input parameter to the map function, but you can get it as a member of the container class. Anyway, you can access the document ID. And then a list of terms. Here, you also need to keep track of the position P of every term. Well, let's start from 1. And simply for all terms in the list, I have to emit the term T as a key value associated to a value part that is actually a pair itself, given by the ID of the document and the position P of the term within the list. And we can also increment P. So, what I'm going to output here is a set of pairs where this is the key. This is what I initially called TK2 as a type, while the corresponding value part so V2 is itself a pair. In our case, TP2 is a word, and TP2 is a pair of integers. If you look at the initial definition of map. And here the mapper is done. What does reduce do in this case? Reduce receives a term and a list of these pairs. So a list of pairs of integer. What does reduce need to do now?
No.
It's going to do absolutely nothing, because reduce already receives this as an aggregate term and the list of all value parts of all outputs of the mapper. So the reduce directly receives this. So if you prefer, it's the identity function. It just needs to emit L as an output. Okay. So what has happened here is that after the map phase, which sent out separately Alice D11, Lods D12, Alice, no, the Bob D2, no, Bob D13, and so on. After the aggregation phase, you exactly get this list. Also, in this case, of course, you can have a combined phase exactly equal to the reduced phase that takes care of an initial aggregation for just the mappers that were executed on the same machine. And in this case, of course, combine and reduce can be exactly the same function, which does mostly nothing. Okay. Okay. If this is more or less clear and you don't have particular questions about this, then I think we can close to this lesson here, so that tomorrow we will see maybe a practical implementation of this and also a few exercises that have appeared in past versions of the written exam. What I might ask you in the written exam about this topic is, okay, I provide a problem and try to define the input and output types of the MapReduce function. Write your functions in possibly understandable pseudocode, something that resembles either Java or some other programming language. And yes, that's all. Of course, here we need to make some assumptions about what is input to the mapper. For example, here I was assuming that the document was already a list of terms, which is fine, because I'm not interested in the details of how documents are tokenized. What you actually get in the Hadoop implementation is that here you actually receive something that looks like a line of text or a whole file, and you need to use a tokenizer class to break it into words. But this is something that you do when you are in front of a computer and not, of course, on a written exam, so that you can make more assumptions in that case. Okay, there are no questions. That's all for today.